So, I mean, this is, as I say, there's probably an easier way to talk about the attractor of a subdynamical system. I mean, um, but well, anyway, um, if we find all of the well, we could just say if we find all of the arrows X from our counting dynamical system, well, let's call them X arrow, from our counting dynamical system to our dynamical system of interest, such that X is in this subdynamical system A. If we then just take the images of each of those, and I'll talk about what the image of a natural transformation is in a minute. Well, at least in this context. I mean, basically, it's just a set of stuff that have something sent to them under this X arrow. And if we take the images of those and do the intersections of them all, then we should get the attractor. Now, we will get the attractor if and only if this subdynamical system A is connected, if it just has one connected component. Otherwise, we'll be intersecting over attractors, because there's a one-to-one correspondence between attractors and connected components. And if our subdynamical system's disconnected, it'll have multiple attractors, isolated attractors, and if we intersect over them, then we'll get noughts, because there'll be nout in all of them at once. What's this image? Well, basically, I think in the category of dynamical systems, if we think about, say, an arrow F from A to B in terms of states, then the image of F is just the set of states of B, such that there exists an A such that F A equals B. Okay. The reason it's so simple is because so, I mean, here's the general recipe. At least I think this is correct. The general recipe for working out the image of an arrow F is we compute the push out of 2 copies of F, and we get this H and K. Whoops. And then we think of this H and K like this. And we take their equalizer. Hang on, looks more like this. Yeah, this is making more sense. So we've got the H and K like this. Then if we take their equalizer, E, then that will be the image of F. And also, since HF equals KF, we have that F is in this equalizer, and then the kind of intermediary arrow is actually going to be the epic in this monoepic factorization. But basically, doing this epimono factorization, I think it's pretty similar to the way it works in set. It's just with extra components potentially. But I mean, in this category of dynamical systems, working out this push out, it's just like taking a co-limit, and the way co-limits work in these categories of functors into set is just like a kind of component-wise version of the way that co-limits work in set. And so, I mean, it's especially simple in this case of dynamical systems where everything just has one internal type, which is star. Well, there's a lot here. Yeah, so we discussed this idea of working out the attractor. There's got to be an easier way. False is the classifying arrow of the empty subobject of 1. Not is the classifying arrow of false. We got a picture of that somewhere, perhaps not. But I mean, think about this. Then we've got true. So what's this not look like? Well, it sends this infinity to, well, okay, let's use orange. Sends this infinity to true, sends everything else to false. That's what not looks like. So somewhere I wanted to make a note of all the things that wanted implementing in a computer. I think this is one formula that does. Maybe this. Yeah, here's a picture of how not works. So we can think of not as an arrow from omega to omega. So we basically have the not of D is equal to 0 if D is infinity, it gives true in that case, and it's equal to infinity otherwise. So that's something that wants implementing. We have a negation of sub-object, which is just the sub-object classified by not of its classifying arrow. And basically that's just going to consist of all of the connected components of our ambient dynamical system, which don't have any bits of A in them. And then not well, not's quite interesting. Basically, if we have a connected subdynamical system, then doing like getting the subobject classified by not of chi of A is just going to be like the sort of closure of that dynamical system. It's going to be like everything that evolves into it. It's going to be the whole connected component of that. So, I mean, for example, consider a dynamical system like this. And now suppose that A is this. Well, then not A, well, not chi A classifies this whole connected component, okay? So it sort of corresponds to the set of states that have chi, the set of states X, which have chi A of X as finite. Okay, and yes, it does, it makes a topology on this category of dynamical systems. So there's different rules that basically, if you have any topos and you have an arrow J from omega to omega, then J corresponds to a topology when it meets certain conditions. And it turns out that J is equal to not always corresponds to a topology. We can think of not the way it works on D. I mean, what we've really got is not of D is equal to 0 if D is finite, D is not infinite, and it outputs infinity otherwise, okay? So we can consider J is not, and yeah, we have a topology. We have J after true equals true. We have J after J equals J, and we have J after and equals and after J times J. So yes, J is a topology. I mean, we don't really need to, well, if we're willing to take the book's word for it, we don't need to show all, this is going through this, they're the three conditions that you need J to satisfy in order for it to be a topology in general. But it's also a general fact that not always gives a topology. Nice thing about topology is that we can form another topos, because I mean, you can really say, what is it? We say something is J true when, I think it's when, oh, I got it written down somewhere. Yes. Like, given a subobject A, the J closure of it is the subobject classified by J after chi A. And so if something, and we say something's J true when it works under this kind of truth area, so it gives us a kind of local notion of the idea of truth. And basically for us, it allows us to think about a kind of simpler topos where we're just really thinking about these kind of closures of dynamical systems and how they interact with each other, rather than concerning ourselves with the intricacies of all of the goings on. And there's a way to form a topos out of that. And okay, in general then, if we have a topology, we say that a subobject of our original topos is J dense when that subobject is equal to its J closure. Okay, so when, in other words, when A is equal to the subobject classified by J after chi of A. So in our context of dynamical systems, and our J equals not, our closure is basically just taking all the connected components that our subdynamical system A touches, and taking sort of all of those as our sort of bigger subobject, our closure. And then to say that